Brought to you by WikiVidi.com. Ultimate fate of the universe. The ultimate fate of the universe is a topic in physical cosmology, whose theoretical restrictions can usefully and scientifically predict the future behavior of the universe as it ages. Based on available observational evidence, deciding the fate and evolution of the universe now have become valid cosmological questions, being beyond the mostly untestable constraints of mythological or theological beliefs. Many possible futures have been predicted by rival scientific hypotheses, including that the universe might have existed for a finite and infinite duration, or towards explaining the manner and circumstances of its beginning. Observations made by Edwin Hubble during the 1920s-1930s found that most galaxies appeared to be moving away from each other, leading to the current accepted Big Bang theory. This suggests that the universe began in the far distant past about 13.8 billion years ago, and ever since continues to expand. Confirmation of the Big Bang mostly depends on knowing the rate of expansion, average density of matter, and the physical properties of the mass, energy in the universe. There is a strong consensus among cosmologists that the universe is flat and will continue to expand forever. Yet many other factors may influence the universe's origin and final destiny, including, for example, the average motions of galaxies, the shape and structure of the universe, or the amount of dark matter and dark energy the universe contains. Theory. The theoretical scientific exploration of the ultimate fate of the universe became possible with Albert Einstein's 1915 theory of general relativity. General relativity can be employed to describe the universe on the largest possible scale. There are many possible solutions to the equations of general relativity, and each solution implies a possible ultimate fate of the universe. Alexander Friedmann proposed several solutions in 1922, as did Georges Lemaitre in 1927. In some of these solutions, the universe has been expanding from an initial singularity which was essentially the Big Bang. Observation. In 1931, Edwin Hubble published his conclusion, based on his observations of Cepheid variable stars in distant galaxies, that the universe was expanding. From then on, the beginning of the universe and its possible end have been the subjects of serious scientific investigation. Big Bang and steady-state theories. In 1927, Georges Lemaitre set out a theory that has since come to be called the Big Bang theory of the origin of the universe. In 1948, Fred Hoyle set out his opposing steady-state theory, in which the universe continually expanded, but remained statistically unchanged as new matter is constantly created. These two theories were active contenders until the 1965 discovery by Arno Penzias and Robert Wilson of the cosmic microwave background radiation, a fact that is a straightforward prediction of the Big Bang theory, and one that the original steady-state theory could not account for. As a result, the Big Bang theory quickly became the most widely held view of the origin of the universe. Cosmological constant. When Einstein formulated general relativity, he and his contemporaries believed in a static universe. When Einstein found that his equations could easily be solved in such a way as to allow the universe to be expanding now and to contract in the far future, he added to those equations what he called a cosmological constant, essentially a constant energy density unaffected by any expansion or contraction, whose role was to offset the effect of gravity on the universe as a whole in such a way that the universe would remain static. After Hubble announced his conclusion that the universe was expanding, Einstein wrote that his cosmological constant was the greatest blunder of my life. Density parameter. An important parameter in fate of the universe theory is the density parameter omega, defined as the average matter density of the universe divided by a critical value of that density. This selects one of three possible geometries depending on whether omega is equal to less than or greater than 1. These are called respectively the flat, open and closed universes. These three adjectives refer to the overall geometry of the universe and not to the local curving of space-time caused by smaller clumps of mass. If the primary content of the universe is inert matter as in the dust models popular for much of the 20th century, there is a particular fate corresponding to each geometry. Hence cosmologists aim to determine the fate of the universe by measuring omega, or equivalently the rate at which the expansion was decelerating. Repulsive force. Starting in 1998, observations of supernovas in distant galaxies have been interpreted as consistent with a universe whose expansion is accelerating. Subsequent cosmological theorizing has been designed so as to allow for this possible acceleration, nearly always by invoking dark energy, which in its simplest form is just a positive cosmological constant. In general, dark energy is a catch-all term for any hypothesized field with negative pressure, usually with a density that changes as the universe expands. Role of the shape of the universe. The current scientific consensus of most cosmologists is that the ultimate fate of the universe depends on its overall shape, how much dark energy it contains, and on the equation of state, which determines how the dark energy density responds to the expansion of the universe. Recent observations conclude, from 7.5 billion years after the Big Bang, that the expansion rate of the universe has likely been increasing commensurate with the open universe theory. However, other recent measurements by Wilkinson microwave anisotropy probes suggest that the universe is either flat or very close to flat. Closed universe. If then the geometry of space is closed like the surface of a sphere, the sum of the angles of a triangle exceeds 180 degrees and there are no parallel lines. All lines eventually meet. The geometry of the universe is at least on a very large scale elliptic. In a closed universe, gravity eventually stops the expansion of the universe, after which it starts to contract until all matter in the universe collapses to a point. A final singularity termed the Big Crunch, the opposite of the Big Bang. Some new modern theories assume the universe may have a significant amount of dark energy, whose repulsive force may be sufficient to cause the expansion of the universe to continue forever, even if open universe. If the geometry of space is open, i.e. negatively curved like the surface of a saddle, the angles of a triangle sum to less than 180 degrees, and lines that do not meet are never equidistant, they have a point of least distance, and otherwise grow apart. The geometry of such a universe is hyperbolic. Even without dark energy, a negatively curved universe expands forever, with gravity negligibly slowing the rate of expansion. With dark energy, the expansion not only continues but accelerates. The ultimate fate of an open universe is either universal heat death, the Big Freeze, or Big Rip, where the acceleration caused by dark energy eventually becomes so strong that it completely overwhelms the effects of the gravitational, electromagnetic and strong binding forces. Conversely, a negative cosmological constant, which would correspond to a negative energy density and positive pressure, would cause even an open universe to recollapse to a big crunch. This option has been ruled out by observations. Flat universe. If the average density of the universe exactly equals the critical density so that then the geometry of the universe is flat, as in Euclidean geometry. The sum of the angles of a triangle is 180 degrees, and parallel lines continuously maintain the same distance. Measurements from Wilkinson microwave anisotropy probe have confirmed the universe is flat, with only a 0.4% margin of error. In absence of dark energy, a flat universe expands forever but at a continually decelerating rate, with expansion asymptotically approaching zero. With dark energy, the expansion rate of the universe initially slows down, due to the effect of gravity, but eventually increases. The ultimate fate of the universe is the same as an open universe. Theories about the end of the universe. The fate of the universe is determined by its density. The preponderance of evidence to date, based on measurements of the rate of expansion in the mass density, favors a universe that will continue to expand indefinitely, resulting in the Big Freeze scenario below. However, observations are not conclusive and alternative models are still possible. Big Freeze, a heat death. The Big Freeze is a scenario under which continued expansion results in a universe that asymptotically approaches absolute zero temperature. This scenario, in combination with the Big Rip scenario, is currently gaining ground as the most important hypothesis. Y. Wang, J. M. Kratikval, A. Linden, M. Shmakova. Current observational constraints on cosmic doomsday. JCAP 0412-006, Astro PH 0409-264. It could, in the absence of dark energy, occur only under a flat or hyperbolic geometry, with a positive cosmological constant. It could also occur in a closed universe. In this scenario, stars are expected to form normally for 1012 to 1014 years, but eventually the supply of gas needed for star formation will be exhausted. As existing stars run out of fuel and cease to shine, the universe will slowly and inexorably grow darker. Eventually, black holes will dominate their universe, which themselves will disappear over time as they emit Hawking radiation. Over infinite time, there would be a spontaneous entropy decrease by the Poincaré recurrence theorem, thermal fluctuations, and the fluctuation theorem. A related scenario is heat death, which states that the universe goes to a state of maximum entropy in which everything is evenly distributed, and there are no gradients, which are needed to sustain information processing, one form of which is life. The heat-death scenario is compatible with any of the three spatial models, but requires that the universe reach an eventual temperature minimum. Big Rip. In the special case of phantom dark energy, which has even more negative pressure than a simple cosmological constant, the density of dark energy increases with time, causing the rate of acceleration to increase, leading to a steady increase in the Hubble constant. As a result, all material objects in the universe, starting with galaxies and eventually all forms, no matter how small, will disintegrate into unbound elementary particles and radiation, ripped apart by the phantom energy force and shooting apart from each other. The end state of the universe is a singularity as the dark energy density and expansion rate becomes infinite. Big Crunch. The Big Crunch hypothesis is a symmetric view of the ultimate fate of the universe. Just as the Big Bang started as a cosmological expansion, this theory assumes that the average density of the universe will be enough to stop its expansion and begin contracting. The end result is unknown. A simple estimation would have all the matter and space-time in the universe collapse into a dimensionless singularity, back into how the universe started with the Big Bang, but at these scales unknown quantum effects need to be considered. Recent evidence suggests that this scenario is not likely. but it has not been ruled out, as measurements are only available over a short period of time and could reverse in the future. This scenario allows the Big Bang to occur immediately after the Big Crunch of a preceding universe. If this happens repeatedly, it creates a cyclic model, which is also known as an oscillatory universe. The universe could then consist of an infinite sequence of finite universes, with each finite universe ending with a Big Crunch that is also the Big Bang of the next universe. Theoretically, the cyclic universe could not be reconciled with the second law of thermodynamics. Entropy would build up from oscillation to oscillation and cause heat death. Current evidence also indicates the universe is not closed. This has caused cosmologists to abandon the oscillating universe model. A somewhat similar idea is embraced by the cyclic model, but this idea evades heat death because of an expansion of the branes that dilutes entropy accumulated in the previous cycle. Big Bounce. The Big Bounce is a theorized scientific model related to the beginning of the known universe. It derives from the oscillatory universe, a cyclic repetition interpretation of the Big Bang, where the first cosmological event was the result of the collapse of a previous universe. According to one version of the Big Bang theory of cosmology, in the beginning the universe was infinitely dense. Such a description seems to be at odds with everything else in physics, and especially quantum mechanics and its uncertainty principle. It is not surprising, therefore, that quantum mechanics has given rise to an alternative version of the Big Bang theory. Also, if the universe is closed, this theory would predict that once this universe collapses, it will spawn another universe in an event similar to the Big Bang after a universal singularity is reached, or a repulsive quantum force causes re-expansion. In simple terms, this theory states that the universe will continuously repeat the cycle of a Big Bang followed up with a Big Crunch. False vacuum. In order to best understand the false vacuum collapse theory, one must first understand the Higgs field, which permeates the universe. Much like an electromagnetic field, it varies in strength based upon its potential. A true vacuum exists so long as the universe exists in its lowest energy state, in which case the false vacuum theory is irrelevant. However, if the vacuum is not in its lowest energy state, it could tunnel into a lower energy state. This is called the vacuum metastability event. This has the potential to fundamentally alter our universe. In more audacious scenarios, even the various physical constants could have different values, severely affecting the foundations of matter, energy, and space-time. It is also possible that all structures will be destroyed instantaneously without any forewarning. Studies of a particle similar to the Higgs boson support the theory of a false vacuum collapse billions of years from now. Cosmic uncertainty. Each possibility described so far is based on a very simple form for the dark energy equation of state. But as the name is meant to imply, very little is currently known about the physics of the dark energy. If the theory of inflation is true, the universe went through an episode dominated by a different form of dark energy in the first moments of the Big Bang, but inflation ended, indicating an equation of state far more complex than those assumed so far. For present-day dark energy, it is possible that the dark energy equation of state could change again, resulting in an event that would have consequences which are extremely difficult to predict or parametrize. As the nature of dark energy and dark matter remain enigmatic, even hypothetical, the possibilities surrounding their coming role in the universe are currently unknown. Observational constraints on theories. Choosing among these rival scenarios is done by weighing the universe, for example, measuring the relative contributions of matter, radiation, dark matter, and dark energy. to the critical density. More concretely, competing scenarios are evaluated against data on galaxy clustering and distant supernovae, and on the anisotropies in the cosmic microwave background. Brought to you by WikiVidi.com. Would you like to know more?